So it's now 4 o'clock Central European time, and it's time for us to start this webinar. I just want to say a warm welcome to everyone to our webinar. Today, this webinar has got the title Optimization of HVACR Systems based on new guidelines to structure data collection from the International Energy Agency Annex 52. This webinar is arranged by ClimaCheck, and my name is Lars Dahlberg, and I'm acting as the moderator. I'm going to guide you through this webinar today. So it's now time for us to take a look at what we will cover today during this webinar. So we have really a full agenda for you, a lot of very interesting content that we will go through, and these are the things that we really want to cover. So how to measure the performance of the air conditioning and heat pump systems using the Annex 52 guidelines, how verification projects can identify savings potentials, how to plan new projects and upgrade existing systems, how this report is relevant for and relates to other types of HVACR systems. So that's really what we're going to cover, but you also have the great opportunity to ask questions. We're going to run a Q&A session in the end of this webinar, and we really do have the experts with us here as speakers. To ask questions, you just check your GoToWebinar control panel, and there you can find a functionality for asking questions. You can ask your questions whenever you want. When you get the question, just type it in, but we will do our best to answer in the end. The rest of the audience will not see your questions, so please take the opportunity. And we expect this webinar to continue for 1 hour. So now it's time for me to introduce today's presenters. So let's see if we can have the presenters online as well with cameras and sound and everything. And here we have one of them popping up. And here we have the second one. So I'm just going to give a quick introduction here because we have a lot of things to cover. So first of all, I would like to present Jeffrey D. Spittler. Jeff is Regents Professor of Mechanical Engineering at Oklahoma State University, where he holds the OG&E Energy Technology Chair. Welcome, Jeff.
Hello, everyone. Glad to join you this morning, even if it has to be remotely.
Yeah, exactly. It's hot over there in Oklahoma.
It was 28 degrees C on Saturday, so yeah, we get by.
We get by. All right, and then we have the second presenter, Claes Berglöf. Claes is the head of R&D at ClimaCheck and the inventor of the internal method for analyzing refrigeration processes patented in 1986. So warm welcome, Claes.
Thank you very much, and nice to see you all.
Yeah, and you're doing the presentations from the Stockholm office where it's not as hot as it is in Oklahoma, but we're getting there.
Yes.
So, exactly. So I'll hand it over to you, Claes. Please take over the presentation.
Yes, so I mean, we think that we are really into a hot topic at this time. We all know that the air conditioning systems and refrigeration system, heat pump systems, they use 20% of the global electricity roughly. And we waste a lot of electricity as they are not working as they are intended to. And we have a lot of history on why we have this situation. But it's going to be measuring and verification that is going to change this. So there are a cost of running them, and it's also the climate impact that is going to make it very important to deal with the efficiency of our systems. And I think that we can clearly say that business as usual does not deliver efficient or reliable operation. There is have been a lot of focus on energy efficient products. So there are product standards, there are high requirements on rating, but this does not automatically mean that they're operating efficiently. And why is this so challenging? I mean, there are many contractors involved to get the system into place. And this is not always easy to get the interaction to work correctly. And in spite of that, there is a huge amount of sensors installed today. Every equipment has sensors, and they are also connected to BMS SCADA system. But there is normally a lack of strategies for measuring and verification and benchmarks. There is a lot of data, but very little information. And the commissioning is many times just done when at the startup, and the building is not in balance, and the loads are not the normal, and the climate is only one climate at that time. So there's a lot of things that are not known when you look at the startup of a plant. And maintenance, then, this is normally checklist based. Somebody goes out and fills out the list, and many times they force the system to run for a short period of time. This does not give anything useful for validating performance. Controls, they are checked at one point normally. A lot of things happens when the load and the conditions change. And we see this every day, that there's so many shortcomings when systems are set up, commissioned, and so on. And this results in high cost of failure and high cost of energy. So when I was informed about this Annex 52, it felt obvious that this is really essential to try to structure this. So this really made me jump at it. And then I learned to know Professor John Spittler, who is one of the co-chairs of this project, and he's really an expert. So I'm very happy to let Jeff take over and give you some of the background of the project and some experiences.
Thanks, Lars. Thanks, Klaus. Thanks, Lars.
Yeah, we can see your screen nicely now, Jeff. So take it from here.
Okay, so I'm going to talk about this International Energy Agency Annex. So the International Energy Agency has a number of what they call technology collaboration programs. One of them is Heat Pumping Technologies, which actually is headquartered in Sweden. And they have a series of research projects that are international and collaborative, and ours was number 52 on this performance measurement. The project, the US and 6 European countries participated. It ran from 2018 through 2021, which unfortunately practically means it's almost done now. We have most of the reports are done and online, but there's just a few that are being finished up now. And the focus is on ground source heat pump systems, but it's really applicable to a whole range of systems. So the heat pump, even though you might think heat pumping technology is only for providing heat, in fact, the technology collaboration program covers heat pumps, chillers, air conditioners, supermarket refrigeration. So it's actually quite broad. And our focus was on ground source heat pump systems, but the work is generally applicable. So the motivation for this project was, for my own part, was partly some firsthand experience I had with the ASHRAE headquarters building, and also a university building in Stockholm that we analyzed the performance of the systems for. But also, other researchers ran into similar issues, similar experiences. There are anecdotal cases of designs that were either poorly conceived or over-pumped is one problem, mismanaged. The ASHRAE headquarters building is a good example, not of a bad performance. The performance was overall very good, but you'll see we found a few things that could improve it and make it better. So I don't have time today to give you a complete rundown on the ASHRAE headquarters building, so I am going to try to skim over the project fairly quickly, but I hope it helps you understand our motivation. So the ASHRAE headquarters building at the time, was since sold because a hospital complex that surrounded the ASHRAE headquarters made ASHRAE a very good offer on it. But at the time, it was renovated in 2008, and there were 2 state-of-the-art heat pump systems installed for heating and cooling the building. So there was an air source heat pump system known as a variable refrigerant flow system serving the first floor, and a ground source heat pump system serving the second floor. And the building was conceived as a living laboratory with over 1,000 sensors. And the idea was that ASHRAE members, ASHRAE is the American Society of Heating, Refrigerating, and air conditioning engineers. So they have a natural interest in how the systems perform. And the idea was that the data from the building would be open to the public, or at least to ASHRAE members, and we could investigate how the system was working. So the air source heat pump system is what you sometimes call a multi-split system. So there are 2 outdoor heat recovery units. There's one of them in the photo right here, and you can see some refrigerant piping on the rooftop. There were 22 indoor units that formed this system, and they had a nominal capacity of about 100 kilowatts. And then the ground source heat pump system is a distributed system with 14 reversible water-to-air heat pumps. So unlike many systems, say in Sweden, where there'd be a central plant with 1 or more heat pumps, in this case, the heat pumps are spread around the building. There's no then hydronic distribution system other than to provide water from the ground heat exchanger to the heat pump. So the heat pumps are spread around the building, and their total nominal capacity is 111 kilowatts. As a result of this system design, most of the heat pumps sit above the ceiling panel tiles, so they're hidden from view. And the only mechanical room is actually a closet, which has, in this case, had a glass door on it so anyone could observe the settings. And here are a couple pumps that are used to circulate water between the ground heat exchanger and the heat pumps. Okay, because there are 2 sort of competing technologies installed in the building, there was quite a bit of interest in the marketplace in the performance. And very soon after it was in operation, various individuals started looking at what we call energy use intensity figures. So an energy use intensity is how many, say, kilowatt hours per square meter does the building consume for the year. And this, or for, in this case, for a month. So you see here, the ground source heat pump in blue, it has relatively low energy usage compared to the VRF or air source heat pump system. So you can see this, most months there's a fairly large difference. Right, and this actually started to appear in the press and advertising and you know, sort of become publicized. So then there's sort of some contentious about, well, you know, is it the system, or maybe the air source heat pump system has a lot higher loads for some reason, right? You really can't tell from energy use intensity figures. So because of this sort of market interest, there was actually enough interest to lead to a funded research project, which you could say maybe had 2 questions that we tried to answer. Do the energy use intensity values represent the system performance? And if so, or if not, why? And we actually went quite a bit further in analyzing this system. So the project made use of over 1,000 sensors that have been added to support the living lab aspect of the building, but also a pretty significant labor effort. So we had 2 researchers with PhDs, I was one of them, and also a graduate student. We spent a lot of hours on this. So we collected quite a bit of data. There's just really too much to show you here, but for example, this is the average power consumption per square meter in watts for the 2 systems as a function of the dry bulb temperature. So when you see these little bars, each one represents what we call a temperature bin. So one of these might be, say, between 21.3 and 21.6 degrees Celsius, something like that. And you can see if you compare the 2 plots, they have the same scale, that the ground source heat pump system actually is using quite a bit less energy over the entire range of operation. And this is just one pair of systems, but still the results were pretty interesting. So we looked at the amount of heating and cooling provided, and for that there was a change in the air source heat pump system, so that we really only able to get this information for, say, the first year of operation. So that's why you don't see red bars over here. So you could see that there's more heating provided than cooling by the air source heat pump system. I'm sorry, more heating provided by the air source heat pump system per square meter than the ground source heat pump system. You see the red bars are larger. For cooling, the values are fairly similar, so not that difference. So to look at system performance and not just what the building loads are, right, we defined something, or, well, we didn't invent this. This terminology has been used actually going back to the 1940s, if you can believe that. Performance factors. So we have cooling performance factors, which are the cooling provided divided by the energy or the electricity consumption, or heating provided divided by the electricity consumption for the heating performance factor. Now, maybe more to the point, this is how we explain it to students, right? It's what you want. I want cooling, I want heating, divided by what you pay for, electricity, right? So when the performance factor goes up, your costs go down. Right? And if we look at the performance factors, right, we can see, first of all, we see that in this case, the ground source heat pump system had significantly higher performance factors in this first winter of operation, right? It's about 3 for the ground source heat pump and about 2 for the air source heat pump. So that was interesting. But another interesting thing, which we'll come back to, is if you look at the first season of operation, the ground source heat pump had about 3 performance factor, and the second season had about a factor of 4. Right? There's a large jump. So we'll come back to that in a minute. For cooling, generally the ground source heat pump system performs better, but not necessarily as dramatically better. So the traditional explanation for this is that the ground source heat pump has better, more favorable entering temperatures. So when it's hot outside in the summer, the ground source heat pumps are getting temperatures around 26, 27 degrees C, whereas the air source might be getting 30 or 32 or even 36. Whereas in the winter, right, we have relatively warm fluid coming back from the ground, but cold air outside. So thermodynamically, that should be better. So that's one explanation, but it doesn't really tell the whole story. The more we looked at it, the more we found that the performance of the ground source heat pump system and the air source, I'm just showing you ground source here, is actually more dependent on the size of the load. So this is a performance factor for both heating and cooling together. Just what's the total heating and cooling provided divided by the total electricity used. This is plotted against the total heating and cooling provided. And what you can see, and again, this is a binned analysis, what you can see is as we get higher load, the performance gets better. It doesn't necessarily go strictly with the temperatures as we might expect from thermodynamics. So I said I'd come back to a couple issues. One was this jump from roughly 3 to roughly 4 for the heating performance factor in the ground source heat pump system. That was caused by the set point of the differential pressure control. So I showed you a little picture of the mechanical room with the closet, and there were some gauges there. And actually, a very astute engineer was visiting ASHRAE headquarters one day, and he said, "Oh, this setting is too high. You really need to lower it." That was during this period. They lowered it, and as you can see, the next winter we got this large jump in performance. Right, and this jump from 3 to 4, this is about a 25% difference in cost for electricity for the system. Interesting, one of Klaus's first slides, he mentioned 30%. Well, here's an example of one setting being 25%. And honestly, this building has really expert owners, and it was commissioned and has an expert maintenance crew. Nobody knew but this one guy that the pressure setting should be lower. So we had to come back to make some field measurements to test this because we didn't install the right sensors when the building was constructed. Right? So I think, as Klaus will probably talk about, it's important to get it right at the beginning. It saves a lot of money and effort. We also found that there was one heat pump that partway through operation developed a stuck reversing valve. The reversing valve changes the operation from heating to cooling. These are cooling performance factors versus the heat pump entering fluid temperature. And as you can see, this orange line is when there was a fault, when this reversing valve was stuck. And the performance factors were quite low for the whole system because that heat pump was operating all the time. And this is a better when it was working. One of the reasons it wasn't noticed is because it was in a stairwell, and I think people don't expect to be very comfortable in stairwells. So very quickly, we found that the performance was contrary to thermodynamic expectations, right? And even though we had really a very knowledgeable owner and maintenance staff, there were still some issues that weren't resolved quickly. So in my view, and of course, I guess I'm a little biased because I did the ASHRAE research project or was the principal investigator for it. The findings were very valuable, but the approach itself isn't widely replicable. As much as I would enjoy getting lots and lots of research projects to study individual buildings, it's just not financially feasible for most owners to pay that kind of cost. Right, and a lot of the cost was due to not having the right sensors, not having things structured right, and that required a lot of effort on our parts to work out the analysis from what information we did have. Also, we used some field measurements, and so it's all very complicated because of that. Right, and of course, there were also some sensors that existed, mainly within the heat pump cabinet on the ground source side, or within the air source heat pump. Actually, there's quite a bit of data being collected. We didn't have access to it. So I think one of the questions is, how could we adjust the approach to make it widely applicable, where it could be affordable for any owner, or at least for many owners, to actually do and get the advantage of this kind of analysis. So this background is really what led us to come up with, or to propose and then actually carry out this Annex project. Right, and the products from the Annex, I mean, they include a bibliography, so I was surprised there was as much information available on existing systems, about 80 publications, although the information was often difficult to interpret because of a lack of standard sort of terminology and standard boundaries for what's being reported. We developed a new boundary schema, which I'll come back to in just a minute, and some guidelines that I think are of interest. Also, there's about 40 case studies published with some open access data sets and about 17 peer-reviewed papers so far. So the instrumentation guidelines were published last fall. It's a 62-page guideline. It covers instrumentation and data, so including where to measure, how often to measure. For like heat pumps or air conditioners, it would be both covers the external method and the internal method. It gives recommendations on sensors, on managing the data, which is a real challenge when you get, you're collecting data every 5 minutes or something for several years and many points, and also on quality assurance of the data. So we're going to make the PDFs available, and there's a link here that'll take you right to that instrumentation guideline. We also have published a set of guidelines on methods for calculating uncertainties. This is a 54-page guideline. I took the lead on this. It may seem a bit esoteric. I won't blame you if you think it is, but it does help explain the required sensor accuracy and also where things can go wrong. And so a classic case is trying to measure energy based on the flow, say to the ground heat exchanger. Sometimes when it's over pumped, particularly, you have very low delta T. It's very hard to measure that, measure that accurately. So one of the reasons for the uncertainty guidelines is just to be able to estimate what it is and maybe know where you're not getting good answers. So again, this is available here. The boundary schema, this diagram shows a couple different kinds of systems, and these dashed lines are the boundaries. And the purpose of having standard methods is so that, and the standard boundaries is so that we can better analyze the performance of certain parts of the systems sort of independently from each other. So depending on the boundary, you can maybe tell, is the heat pump working well? On another boundary, you might be able, if you're looking at going from one boundary to the next, you might be able to tell, oh, our distribution system is using a lot of energy, and that's why the system performance overall is so poor. So a lot of thought went into these, a lot of international expertise input went into developing these boundary schema. So they can be used for different things. And then I mentioned there are about 40 case studies at these locations. They cover a lot of types of systems. They're all ground source heat pumps, but some use vertical boreholes, some use open groundwater or open loop systems, and some use energy piles beneath the buildings. There are still a few case studies coming, but there are quite a few online. So we should have about 40 in total. Okay, so there's still a couple guidelines that we're working on. They should be done, I think, in the next few months. There are still a few case studies that are being edited. They'll be published soon. You can see the website here. You can also contact the operating agent, Dr. Jalin, or myself, the co-operating agent. So with that, I thank you very much for your time, and I'd like to hand it back to Klaus.
So thank you, Jeff. Before we hand it over to Klaus, I just want to mention to everyone that you will get a copy of the presentation in PDF format in an email that we will send out tomorrow, so you can have access to all these links and things. But also, please remember that you have the opportunity to ask questions for Jeff and Klaus. Ask them whenever you want using the GoToWebinar functionality for asking questions, and we'll have the Q&A in the end of the webinar. So with that, it's time for me to switch over so that Klaus can continue with the presentation. So I'm switching over to you, Klaus, now. Yes, now we can see your screen, Klaus. So take from there. You have to unmute, Klaus.
Sorry, two things.
Yeah.
One too much. So thank you very much. And yeah, so I think that Annex 52 really have been good learning for us. And I mean, we have measured, or I've been involved with performance measurements for more than 30 years. So and the challenges has been very obvious to me. And what we see is that there is a certain amount of focus on balancing fans and pumps and so on. I wouldn't say that it's well done at all the time, but this is all systems have some kind of balancing. Then, of course, with today's situation, when you're working with variable flows, it might be not very efficient to do balancing before you commission your plant and hope that that's going to be useful for the life of the building. But there are some focus on that. But then, I mean, why I started with this was that there is such a neglectance of the heat pump or air conditioning refrigeration system. It's assumed that that works as rated. And in reality, that is not the case. And this represents often 60% of the energy that's consumed by the system, and you still assume that it's working. See if I can get this to change slide.
Just click on the PowerPoint and then it can.
Yeah, that's what I did, but as I made a laser pointer, it seems to stop moving the slide. And so I removed the, I apologize for this.
Try the keyboard.
Now, okay, so I mean, by looking into what happens in the air conditioner refrigeration heat pump system, you address the whole bit that people have not looked at before. And this, as this is a majority part of the energy, it's really important to be able to do that in detail. If you can succeed in measuring on the outside with flow-based measurements, that if you measure correctly, even on small temperature differences, that is useful information. But it's a challenge that you don't know what the problem is. So this is where we came from, is to look at how does the machine work, and then also, of course, what it does in the system. So we find that there is a huge saving potential. We have experienced from thousands of sites, and I would say that between 10 and 40% savings are possible. This is not by replacing system, it's by making the system that you have to work better. A lot of it is very low cost measures that you do. Sometimes, of course, there can be a compressor that has a problem, and it's much cheaper to repair it than run it to failure, which is the normal situation today. So we are in a situation where people take write protocols or tick boxes, and you have BMS SCADA systems that are assumed to deliver information on when things are not working well. But these are mainly alarm handling. They will tell you if the pressure goes too high, too low, if the current goes too high, but they rarely have much to do with efficiency. So we needed better guidance and better standardization of what we do, because there is a lot of information in the sensors that are already there or can easily be added. And so, of course, it's the trend that we need to push is to make information out of the data, make it easily available. And then, of course, energy information related to outdoor temperature is essential to work with optimization. So we have both the performance side and the energy side that we need to track much better than what has been done normally. And this is, of course, going to change how things are done when we have much more information available, and especially by bringing it up in the cloud where it can be cost effectively handled. So what ClimaCheck is working with, just for those that are not very familiar to what we do, we have cloud-based analyzing tools that take data from systems all over the world, and we have inspection tools used for troubleshooting, performance inspection, energy optimization in the field. But the trend is, of course, to go to using cloud-based systems where it can be done 24/7. And data can come from a specific sensor that are installed just for performance analyzing of the air conditioning, refrigeration, heat pump system, or it can be data that is already collected in the BMS SCADA system, which is today in a building that is built. There will be a lot of sensors in the air conditioning, refrigeration, heat pump system. In the controllers, they have pressures, they have a lot of temperatures, they very often have current or power. And the BMS system adds an additional layer of information. So it's essential then to use this in a good way. And there are standardized protocol like Modbus, BACnet, and this type of protocols. So you can extract the data to a gateway that transfer it to the cloud. And then the result can be returned to the gateway and read by the BMS system. Of course, the gateway can read from controllers that are Modbus capable. And more, we also see that there are server-to-server communication, where you have a web-based system that's connecting a lot of sites, and that web-based system can then send data to another server that is doing the analytics. As many web-based portals, they have some specialties, but none of them are the best for all applications. And I think that ClimaCheck Online has a lot of expert knowledge on air conditioner refrigeration systems. And as Jeff mentioned, Annex 52 had both cover what sensors are needed for what's called external method, or that's a conventional flow-based measurement. So you need a certain number of sensors for that. And in that, the refrigeration process is a black box. Whereas if you look at the internal method, it allows you, by taking the pressure sensors that are not in most equipment today, as well as temperatures that are frequently already in the unit, and then using the same temperatures on the secondary side, so it can be air, water, or brine. By combining these and doing the thermodynamic analytics, you can get complete data on the performance of the system. So these are the basics of any training in refrigeration or thermodynamics. You can calculate the process when you have the pressures and temperatures. And then the trick with the internal method is to use the compressor as a flow meter. We know that the energy laws apply, so if we put electricity into a compressor, it comes out as enthalpy change. Then we can calculate the mass flow of the refrigerant, and then we know the heating capacity and cooling capacity. But the best part of the story is that we also can define the compressor isentropic efficiency, condenser efficiency, evaporator efficiency, cycle efficiency. So we know where we have a problem, and we also can follow all the KPIs in the system, like superheat, subcool approaches. All these points will make it possible to, in real time, detect any deviation that affects the performance in air conditioning, refrigeration, heat pump systems. Anything that affects the performance can be detected in real time. So what the internal method focuses on the system boundary 1 and 2 that Jeff referred to, which is the refrigeration process as such and the primary pumps. But there's obviously no problem with adding the distribution pumps and fans and so on, and calculate further system boundaries. But the focus is typically more on system 1 and system boundary 1 and 2. And then when you have this information, it's possible to express any system with the efficiencies instead of looking at COPs or kilowatt per ton or whatever performance indicator people are used to. And the advantage with looking at efficiencies is, of course, that the conditions will always change for a heat pump or air conditioning system. So you might have COP3 in the morning and COP6 in the evening on a system that is as efficient because of that the conditions change. So this makes it, of course, much easier to understand without having to know all the background in thermodynamics. You can see if your system is changing in efficiency. And you can, of course, put automatic alerts on any deviation that occurred in the system. So this gives us an easy way of visualizing something when we're talking about efficiencies rather than the specific values. Then, of course, all the values that people use to evaluate an air conditioning refrigeration system to make it a professional maintenance control would, of course, include subcool, superheat approaches and so on, and delta T's and flows. All these are, of course, also established and can be monitored. And then Jeff showed some data with the energy consumption at different outdoor temperatures. And this is an extremely powerful tool when we compare systems and we compare when we implement measures on a system. When we work with optimization of an air conditioning refrigeration heat pump system, we are going to have a big challenge with that yesterday is not the same temperature as tomorrow. Whereas if we use the energy signatures, as Jeff showed you, we will, for every outdoor temperature, we will have a certain energy consumption. That's the red bars here. If I take the statistical values for these, I get the signature, which is the energy signature for the building. And when I then do some measures to optimize this, and I reduce my energy consumption, I get a new energy signature. The difference between these two is the energy saving I achieved, taking the different operating conditions into account. So this becomes a very powerful tool, both for optimization and for catching if I have a deviation. If I have a deviation, but in energy signature, but I do not have a change in performance, then I've changed my load. So it helps a lot with troubleshooting. And that, I think, is the key to bring data together so you can cost effectively pinpoint the problems. And an air conditioner refrigeration system is quite complex, even though there are not that many components. And I mean, we only need 10 sensors to evaluate the process. But there are quite a few things that can go wrong. And unless you have good measurements, it can be challenging to identify what is wrong. And as every degree in changed operating conditions has a major impact on our performance, it's critical to keep monitoring all parameters in the system to avoid that you have excess energy consumption, or that something starts going wrong that will result in a failure in the near future. And one of the key things that was also discussed in Annex 52 is, of course, that you need to not only measure one of the, not measure the whole system as one, or just focus on one part. You need to understand what is causing what in the system. So I think that you need to break up your system, understand it, and then be able to detect what part is deviating. So that is the basics to then later be able to benchmark the different components. So if one system would have much higher auxiliary loads, then we need to know that it's not just a lower performance in total, but it's because the auxiliary loads are unproportional in the system. And we see that a lot of the issues we come across are related to that things are done as they have always been. And there is a lot of things that are ending up between different contractors. Somebody explains that this is because of this and so on. And there are different challenges with who's owning the equipment, who's paying the bill. You have it can be difficult for the operational staff to get financing to improve things and so on. So you need to take a holistic approach and look at predictive maintenance, where you're using all this information to create efficient operation and drive what's called continuous optimization. If you have the data available, it's much more cost effective than if you go out and try to gather data and then make analytics. We have tried to, based on our experience, give a guide on how you implement predictive maintenance in an organization. So this is available in the presentation. When you get it, you can click on the link here if you're interested in that. And US Department of Energy, they have said that you get 10 times the investment back if you invest in predictive maintenance. You can remove 75% of the failures. So there is this is going to be the future, but we have to change how we do things. So related to the Annex 52 is points 3 and 4 in our guide is to define the data collection requirements. And I would say that it's almost zero cost if you do it when you make a new project. Whereas if you have existing buildings, you need to look a little bit more closely, because of then it can add what sensors can you use, can you access those sensors and so on. But the first step is, of course, to establish a strategy in an organization on how we work with data. I'm just taking some few very practical examples. This is from a hotel in Sweden, they had a number of compressor failures, and eventually they installed ClimaCheck on the system. And here we can see how the compressor efficiency suddenly could just go through the roof. This is obviously not that the compressor got very good. But if I see here, my subcool went very high, which made the expansion valve not work correctly. So it flushed liquid back and broke the compressor. And it broke because of that. The liquid refrigerant went into the oil became thin, ended up in the compressor, and then broke the gasket. And before it had broken some valve plates with very high cost. So it's a very practical case where you can monitor these parameters, that your superheat disappears, your compressor efficiency goes up. So this can be detected so it doesn't happen many times, because normally compressor might survive the first time, and then next time it's more severe and it kills the compressor. Leak detection is, of course, also very important. For those that have been working with leak detectors that are installed on site, it's quite challenging to put the leak detectors in a good place, but a leak will affect the operation of the plant, and it can be detected. It can vary a little bit from system to system, but typically subcool is a very good indicator on the leak, on the charge in the system. So if there is a leak, the charge changes and your subcool change. Also, superheat is a good indicator. And eventually, you will get an impact on your energy consumption. Then you can catch this instead of waiting for the scheduled visit to the site where it would be detected. In Europe, this if you have a monitoring system that catch leaks, you can reduce the on-site leak detection to half. This is a case where the condenser efficiency just suddenly drops at certain conditions. So it looks fine most of the time, but at some conditions, in this case high condensing, when the expansion valve, which is unstable here, when that closes, it builds up liquid in the condenser, which pushes up the pressure. All these can be monitored and detected automatically. And it avoids that this system would trip at high ambient. Controls is a terrible state on many sites. Here is compressor on and off, which kills the compressors, but also the evaporation is fluctuating with more than 10 degrees. And as every degree means 3 to 5% difference in performance, it's easy to understand that this is not an efficient operation. Here is an example from a state-of-the-art, newly installed CO2 system with variable speed. It's modulating continuously, starting and stopping compressors. We complained, nobody wanted to do something. They broke 2 compressors before they adjusted the controls. This is a typical installation with an aquifer used both for heating and cooling with 2 units. At some loads, we have short cycling of the compressors. That results in that the system is throwing oil out into the system, ends up in the evaporator, doesn't come back. The system is tripping on oil protection. We can also see that the expansion valve is not able to handle the variation in capacity well. So these are all parameters that are normally not monitored, but they can easily and cost effectively be monitored. So now I hand over to Lars, and I hope that somebody had some questions.
Yes, we are going to move into a Q&A session now, where you have the opportunity to ask your questions, and we'll do our best to deliver the answers. So check the GoToWebinar control panels. You can find the functionality there for typing in your questions. And we'll see if we'll get any questions. And yes, as I said earlier, you will be able to get a copy of the presentation in PDF format of presentations. We'll send out emails tomorrow. You'll also get a link to recording if everything goes well with that. I can see the questions coming in about that. So, and the contact information. So you will get that, and also link to the guide that Claes was talking about. So let's see now if we get any questions. Whatever questions are interesting, always. Well, we don't have that many questions coming in, so we'll see. Here comes a question. So let's see. To what extent do current chillers, heat pumps, have the necessary controls? Yeah, I wonder who wants to answer this one.
Claes.
Is it Claes?
I think that today, I would say that I mean, most modern sensors, most modern units would have all pressure sensors needed. They would have, most of them, all temperature sensors except for one. And then power is, there is more and more sub-metering, but as standard, I would say that you need to take into account how to measure power to make a good measurement on a refrigeration process, because you need to have power per refrigerant circuit. So you can have multiple compressors. You don't need to measure every, but if you have a 2-circuit chiller, most standard would be that you put one power meter for the whole chiller, whereas we would want to see power per refrigeration circuit.
Okay, I hope the answer was okay there, but let's move on with the next question. This is a relatively long one, so listen up. Hello, in a system where the chiller has a dedicated oil cooling system, as an ammonia system with liquid cooling or a thermosiphon, does the internal method gives useful information?
That's a clever person who wrote that, who knows what he is talking about. Yes, I mean, I didn't mention because of the time that there is a small heat loss from the compressor shell. So when you do the energy balance over the compressor, you need to take into account any cooling of the compressor. On semi-hermetic and hermetic compressor, this is a small and fairly constant factor, so it doesn't cause any problems. But when you have active cooling, as this question point to, then you need to have information on that cooling. So we have, I would say, models for all to me known coolings. I mean, if you know the oil flow, you can measure the temperature difference on the oil. If you know if it's water cooled, you can measure the water flow to the cooler. So we have anything from based on equations for certain compressors, based on manufacturer data to where we measure the flow. So it can be handled very efficiently, but it needs to be handled.
Okay, so thanks. Next question. Is AI able to replace the analytical method in the future?
I think that we are, of course, working with, for one thing, I don't like the vocabulary AI because of it's such an unknown what that is. I prefer automation or machine learning, but certainly we started to implement machine learning to reduce the engineering work required to detect. We can detect any fault, but it requires that you set things up. So by using machine learning, you can reduce the time. But the biggest problem with machine learning or AI, I think, in air conditioner refrigeration systems is that if you create too many false alerts, then you are going to destroy the possibility of using it. So where we look at, for example, isentropic compressor efficiency, if you would not first calculate the isentropic efficiency, the challenges with detecting a compressor problem with AI is going to be immensely much bigger, because you have then you have so many parameters that are affecting your compressor efficiency. And if you calculate the isentropic efficiency first, you know how the compressor should behave. You don't need to train your compressor. You don't need to train your AI to detect the change without giving false alarms. And as there are hundreds and thousands of different compressors working at very big envelopes, I think it's a huge challenge to catch and pinpoint problems based on just inputs. But if you have the model of the system already, you can, I mean, you don't need AI to detect compressor efficiency issues. Those are there, you can measure them. So, I mean, to sort out everything that can be directly measured and don't need AI is, of course, a huge step. Then we'll use machine learning and AI to reduce the engineering time and to detect other things that are quite challenging to detect automatically without using machine learning. So we are working on this every day, and we have taken some steps, but there are many left.
Okay, thanks for that. So we have quite a lot of questions left. We only have like 3 or 4 minutes left for this webinar. If we don't have time to answer all the questions, we will be able to get back to you and give you answers one-to-one afterwards via email. So keep sending in the questions. That's kind of what I'm saying. So let's move on and take another question here. This one starts with, hi, Claes. The energy performance is only done with the dry bulb temperature. What about wet bulb in chillers with water condensing?
Yeah. Once more, that's a very good question. I mean, we calculate the wet bulb. We are working very hard. We have quite a bit of cooling tower analytics that we are doing. Currently, we are doing them not online. I mean, we have the wet bulb, of course, and so you can visualize that. But we are working very hard. We have a big project with cooling tower analytics, where you take all those aspects into account. So it's work in progress when it comes to the cooling tower and evaporative condensers and adiabatic condensers. So that is very relevant, and it affects also, I mean, things like the energy signatures and so on, where I mean, you need to know that you take that into account, but exactly how that is going to be visualized in the future, we will have to come back to in a month.
Okay, we're almost running out of time, but let's try this as our last question and see if you have time to answer quickly, Claes or Jeff. Do the heat pump suppliers, Thermia, Nibe, and others, cooperate with recommended maintenance like what you, ClimaCheck, offer, please?
We have very good relation to all of them. I mean, we all of them have been different ways been using ClimaCheck at times. So we have good relations. They have their interest and they experience what the customers require. They have not experienced the requirements for predictive maintenance in any meaningful way yet, I think. So they have apps, they have some data. I would say they have no, I mean, they don't have things like compressor, condenser, evaporator efficiency or things like that. They don't. We do calculations on the data they have.
Okay, so that was the last question that we had time to cover. The other questions that we haven't been able to deliver answers for, we will come back to you one by one and deliver answers via email. So I would like to say big thanks.
Yes. Just one thing. I think that, I mean, we could try to if you send those questions to me, I mean, if some are of general interest, I can answer them and you can send them out.
Yeah, we can do that as well. When we have summarized it, we can send it to everyone. Yeah, we can.
I think that many of the questions so far, I think, has been very, I mean, coming from people who know where the problems are. So I think that many of the questions might be general.
Yeah, we can fix that. So before we close down, I just want to repeat, you will get emails tomorrow, or one email at least, with a copy of the presentation in PDF, link to the recorded version, and also link to the guide and contact information. So with that, warm thanks to everyone that took your time and joined our webinar today. And also thanks, maybe some final words from Jeff and Claes before we close down.
Thanks, everyone. Appreciate your time.
And thank you very much for spending the time on this webinar. And feel free to send us emails if you have questions that can come up tomorrow.
So thank you. With that, we are going to close down the webinar for today. So be careful out there, and bye-bye.